Hi, my name is Anand. I'm a manager, customer advisory at SAS Institute. And today in this talk, we are going to build an automated CI/CD pipeline for a machine learning project. In this demo, we are not going to necessarily focus on a specific SaaS product or the capability. Instead, we are going to integrate and create an automated pipeline using third-party software stacks, open source toolkits with SaaSwire. And for the demo, we are creating a demo around a fictitious project called Awesome Model, and that will be our project that we are creating from scratch. So before we begin, let's define what the final objective is, right? So we want to take the models that we are working on, the project that we are working on, from our laptops, workstations, dev environments, and we want to take them into production in a very reliable and repeatable manner, in a manner that our organizations and our peers can trust the decisions that are being made using the models and analytics that we are producing. So in the demo that we are creating, we want to achieve a couple of things. Number one, we want to eliminate snowflake effect, and that is, the case where you say my project or my model works here. I have no idea why it's not working in a target environment or a production environment. And that can happen because of multiple different reasons, right? You may have a hard coded string that is not getting resolved in the target environment. You may have a mismatched version of, let's say, a Python module, which may not exist in the target environment, or maybe the versions are different. We also want to maximize the creativity. We want people to be able to contribute and enhance what we are working on without the fear of breaking changes, right? It is observed that once a project goes beyond a certain complexity, people are fearful of making changes. And that's just not acceptable, right? You want to foster innovation. We also want to create a pipeline that is agile enough so that we can quickly go back in time to a previous version of the model and then again fast forward back to the latest version. So we want an agile pipeline, and we want to make sure that once we have created something that we kind of like, we should be able to quickly deploy it in production without any manual intervention. Because taking models and putting them into production is hard manually, and we just want to eliminate all of the human error that can happen. And again, the final objective being we want something that is trustworthy, where the organization can have confidence because they will be using these models and analytics that we are producing for making decisions. So let's look at a typical CI/CD pipeline for a machine learning process and pipeline. And everything starts with a Git repository. And in our case, we are using GitLab. And this is where innovation happens. This is where collaboration happens. And we want to capture each and every aspect of our project, the source code that we are working on inside this Git repository. Secondly, we not only want to capture what we are creating, a good pipeline is a pipeline where we are also able to capture all of the parameters and environment variables and information around the runtime that is going to execute our code should also be captured inside this repository, because you want to isolate and eliminate all of the variables that can have impact on the outcome of the code that you're creating. And once you have this repository and this rigor around a Git repository in place, you're in a position where you can integrate your Git repository with a CI environment, which is continuous integration. And the whole intent here is that you want to make multiple different commits every single day when you're working on the project, because that allows you to fail fast. Because the commits are small, you can even isolate the problems faster, fix them. So fail fast and fix fast. And that allows you to have your project always in a state where it is completely functional. And that doesn't really stop there, because a good pipeline is a pipeline where you're not only checking for the correctness of execution, but also what the outcome is should also be checked if it is correct or not. So when we're talking about a model, you want to check the accuracy of the model. You may want to write test cases that validates the functions that you are writing for let's say data transformation. And once this process is in place, then you are ready for continuous deployment, which is the last second phase. And in continuous deployment, the intent is not that you will be deploying each and every iteration of your project in production, but you want to be in a place where should you choose to deploy any specific commit, you should be able to just, with a click of a button, able to deploy the model that you have created. And to close the loop, last is how do you monitor your model that has been put into production? Do you have facilities in place where you can measure whether the model is drifting or decaying? And if it is decaying, what remedial actions can you take? It can be refreshing the model, or it can be retraining the model with new data set. So this is what a typical CI pipeline looks like. And a good pipeline is a pipeline that can integrate whatever tools your developers are using, because an analyst today has a choice of so many different tools, and you will have to make multiple different decisions as to what tools constitutes your pipeline, your environment. You may have a SaaS programmer using SaaS Studio, or a person who's coming from an open source background using Jupyter Notebook or Visual Studio Code. You will have to decide on what platform will you use for version control, what runtimes you're going to use, where these runtimes are going to get executed, the CI system of choice, where the deployment of the model would take place from a cloud perspective, and how you're going to monitor. So case in point is there are multiple different tools, and hopefully by the end of this presentation, I am able to convince you that the integration points that Vaya provides are powerful enough that you can really stitch up any pipeline that you would want to create using all of the tools that are available out there. Of course, you can always go back to the APIs and write your own API calls to integrate. But we have also gone ahead and created some really nice higher order applications that you can use from within your programming environments. And some of the tools that we are going to use today are, for example, we have SWAT, which is a Python package that allows a Python programmer to connect to a cloud analytics service, which is the Vaya Compute Platform, to interact with the data that is loaded in memory and use the analytics and analytical procedures that Vaya provides. We are not going to use DLPy, but DLPy is also a pretty awesome library where you can import DLPy in a Python environment where you have ready-made pre-trained models that you can augment using your smaller data set for deep learning problems like computer vision and natural language processing. From a model management perspective, again, we have SASCTL and PZMM. Python libraries that you can import in a Python environment to interface and interact with Model Manager. You can publish your open source model to SAS via Model Manager, and you can interact with Model Manager right from within your Python interface. The last two libraries, which is SAS via, which is basically a CLI, extremely powerful CLI that allows you to manage various aspects of Vaya platform from within command line interface. And a person who's coming from an operations background would absolutely love it, because you can wrap it up in your scripts and automate in a programmatic manner tasks that you would want to perform on Vaya. You can completely eliminate the use of user interface and point and click if you want to automate a task. We will be using that to submit a SAS program to a Vaya environment remotely to workload manager, and then wait and capture all of the outputs. And last but not least is MAS, which is Micro Analytics Service. It's a really cool piece of technology where you can take your models that you have trained, open source or SaaS, operationalize them, wrap them up in container, and serve them up as a service with an API endpoint. And since these are stateless, if you have a lot of calls, you can easily scale them by adding more replicas. So these are the components that we are using. And as I said, you can always go back to the APIs and make specific API calls if you want to do something more sophisticated. So let's look at the demo. The demo is of a fictitious pipeline, which is awesome model. And the second half of this image shows a logical view of what a pipeline would look like in a deployment. Again, there are multiple different choices as to how would you train, whether you're going to use GPUs or not if you're using deep learning models, if the training is going to happen in batch or distributed manner, how are you going to evaluate? But what we have distilled out is shown on top. We have 4 different stages. The first stage is the build stage. Exploratory data analysis, training of the model, and deployment. The way our demo is going to work is as soon as a commit happens in our Git repository, the first thing is a runtime container is built using the specification that is defined inside our project. So we are going to build a Python runtime. We are going to install all of the libraries with specific versions that our project depends upon. And we are going to persist this container in container registry. Second, we are going to use the same container that we have just built to execute a pure Python program that performs data profiling. Third, we are going to take a SAS code that a SAS developer has developed using SAS Studio, and we are going to submit that code to a SAS Wire environment using Workload Manager, execute in a SAS Wire environment, capture all of the output back, and persist in our Git environment. 4, we are going to train a classifier, a model using XGBoost, Python, open source model. And then we are going to use SAS-CTL and PZMM to take this model that we have trained and register it in Model Manager in a SAS Wire environment. And last but not least, once the model has been registered, we are going to again use a Python interface to operationalize the model that we have just registered in a microanalytics service. So we are going to spin up a container and start serving the model. We are also going to do a very quick test to see if we can score using that microanalytics service to see if everything is functional. And last but not least, at every point in time in the entire pipeline, we are going to persist the outputs created by each of these tasks for a couple of reasons. Number one, if you want to go back in time and see, at version 1 or at commit XYZ 10 weeks back, what was the output? Is that output different from the output today? You can do that without executing the entire environment or entire pipeline back in that time. You have complete lineage as to how the project evolved and what the outputs were and how outputs started changing. So it's all about building trust and transparency. So the whole demo is distributed in 2 phases. The first persona is that of a SAS programmer who is logging into a Wire environment, opening up SAS Studio, and working on the project from a SAS Studio environment, which is connected to a Git repository, works on the environment, and commits the change. So let's look at the first phase of the demo. So here is our awesome model project in GitLab. And the persona is that of a SAS programmer who is working on an exploratory data analysis. So we will go ahead and clone the repository, copy the link, and go back to SAS Studio programming interface. Here we are going to clone the repository, paste the link for the repository, create a new directory. Let's call it awesome model. And there you have it. Now we'll clone the repository and you will see the assets from that repository will start showing up here. And on the right, you will see the Git interface for SAS Studio. Now here you will see all of the commits along with the messages that it was for each and every commit. If you click on a specific commit, you will see all of the files that have been modified and what modifications were made. Now, since this is a fictitious project, we will open up a SAS program, which is exploratory data analysis for the HMEQ dataset. We load up the data. Here we are plotting some graphs for missing values. We will impute missing values using this block. We will identify the variables that explain some variance. Let's just go ahead and execute this code. Now, once the code is executed, we will have our report in front of us. And this is the output from this exploratory data analysis job. You can see the plots that we were talking about for missing values, for variables that explain the variance. If we come down, we can see ROC and the lift charts. So let's go ahead and make some modification in this code. So let's just scroll down all the way to the end. And the last block of this code is to plot the lift chart. Let's go ahead and comment out this block. Let's assume that for some reason we don't want to show these plots in our output. We save the chart, we execute, and once we have the report, we should be able to validate whether our lift charts were plotted or not. Okay, good, one single plot. Okay, perfect. So now I think we are satisfied with this code here, and we will go back to our Git interface. And if we click on commit, we will see all of the files that have been modified. We will stage this change, add a message, remove the lift plot, and perform a commit. Now, once we push the commit back to our Git repository, we can go back to the Git interface and see the pipeline has automatically triggered and has started. So if you click on the pipeline, we will see the first job is to build the Python runtime. And the second job in the second column is the task that is responsible for executing the SAS code that we had just written. So let's refresh, and there you go. We will click on the workload manager task, and now the Python runtime and the runtime, Linux runtime, is getting downloaded. And now here we are submitting the job to a SAS Wire platform. Once the job finishes, you will see on the right-hand side, we are collecting all of the artifacts that are being produced by this job. So you can either download the artifact or you can just browse them in place. We click on the artifacts, and here is the output. If you open up the output, it's exactly the same output that was being produced in the SAS Studio session. It's just persisted and tagged with the specific Git commit. So if we click on the pipelines, you can also see all of the historic runs of each and every pipeline that was executed along with the artifacts that were produced. You can go back to the historic runs for every commit. You can see which pipelines failed. And if you wish, you can further investigate why a specific pipeline actually failed. So that's about it for the first persona, which is that of a SAS developer. And now let's talk about the second persona, and this is of a person who's coming from an open source background. So this person is using Jupyter Notebook, and this analyst is going to build a XGBoost model, publish it, and operationalize it and deploy it in mass container, all from within a Jupyter Notebook. Once that person is satisfied with the creation that he has created, as soon as we perform a Git commit and Git push, the CI/CD pipeline executes and follows through the entire process that we have just defined, which is to build a container, perform exploratory data analysis, build the model, and deploy. Now, the second persona is that of a data scientist working on training a classifier using Python stack from Jupyter Notebook interface. And here's the requirements.txt file that specifies all of the libraries that must be installed in the Python environment for the project. Notice that we are specifying the versions of each library, and that allows us to ensure that the runtime that we built is deterministic each time it is built. And in the project, there are three notebooks. Profile data, it's a very simple, pure Python code that generates a data profile. Lone default predictor trains the classifier in Python and registers the resulting model in SAS via Model Manager. And publish default predictor deploys the model and performs a simple validation check by scoring a record. Now, let's log on to Jupyter Lab and execute these notebooks one by one. Here is the same file system tree. We open up our notebook subdirectory. And the first notebook is profile data. As I said, it is a very simple Python program to profile the data and show the trends that it identifies in the data. It will generate a nice HTML report. And you can see all of the columns that it identified, the kinds of column. And if you toggle for detail, you can see various statistics around that column, distribution of this categorical variable. You come down, there are very nice charts showing correlation between different variables, missing variables, heat map around missing variable and their relationship with other columns, and a basic chart to show where the missing records are. So let's open up the second and more interesting notebook. And let's also go ahead and execute the entire notebook. And then I can describe the notebook. So if you look at the library of imports, the two libraries that I briefly talked about, SWAT, that allows you to connect to cloud analytics service in via the computation platform from Python, can be made using SWAT. SASCTL is a library that allows you to interface with Model Manager, publish the models. Now, if you scroll down here, we are loading up the data, splitting them into training, validation, and test subset. We define model attributes where the model needs to be saved, what is the name of the model, and other attributes to go along with the model. We are defining the input and output variables here. And this is where we have built the XGBoost classifier. And along with the classifier, a sample source code for how do you score using the pre-built classifier and the pickle file. Now here we are creating the project in Model Manager and then creating a new model version and registering that version into Model Manager. And since the project was already there also exists some other models. So we are going to register this model as a new version. And once the model has been registered, we can go ahead with the third notebook. And this notebook is again going to use SASCTL Python library to publish that model. And once the model has been published, we are going to score that model using a sample record to see if everything is functional. There you go. Now, let's go to the Model Manager interface. And here we can see the project that we were working on, Awesome Model. And if we open up this project, we should be able to see the model that we have recently published, which is the lone default HMEQ. We open up the model, and we can see all of the 9 versions that have been registered and the model versions that have been published into Model Manager. Here are the properties that we defined in the Python code to go along with the model definition. The variables, defining what the input variables are and what the output ones are. And here are all of the artifacts that have been registered along with the model, source code, and the actual pickle file. So now let's just save all of these executed Python notebooks, and they will constitute as changed code. So we should be able to go and make a commit to Git, and that is going to trigger a new pipeline execution. So here we are committing the changes and pushing the changes back to the Git repository. So as soon as we push the commits and refresh our interface, you can see that the pipeline has started running. Let's go ahead and click the pipeline. Now here we are building the Python runtime that is consuming requirements.txt file. So it's installing Python inside a container. Once Python is installed, it is going to install all of the libraries that we specified in our project. Now we are executing the pure Python data profiling notebook. And once that's done, the second one is going to be the same code that we executed in the previous part of the demo, which is submitting the SAS code to SAS via environment using Workload Manager. Now our exploratory data analysis is completed. Now we are training the model using the second Jupyter notebook, which is Lone Default Predictor. And last but not least, now we are deploying the model that was published inside Model Manager. And this phase is also going to perform a simple and very quick validation to see if we are able to score using a sample record. And once that's done, the pipeline would be successfully executed. So if you go to the container registry, every time we are building our Python environment, you will see that there is a container, a runtime container that has the exact same name as the SHA for the Git commit. So if we go to the tail end, you will see we have this container that is associated with each individual commit. And the whole idea is that if we are reverting back to a prior model, we don't want to find out that, when you install Python, the library versions have changed and the outputs or the outcomes are slightly different, or even worse, they're not working. So now we are browsing the artifacts that were produced by our pipeline. And this is the data profile that we created, the HTML file. As you can see, is still there. And now this is the execution that is associated with that specific run of the pipeline. Let's go back to the pipeline and look at the model that we have created. So first, you will see that there is the persisted output of the notebook itself. And if you go back up, we are also preserving the pickle file that was generated along with all of the artifacts to support the model, including the score code. So now let's go back. So all of these pipeline steps and stages are defined in a very simple YAML file. You expose the variables that you want to use, then you specify the stages, and then you associate with each stage the exact command that you would execute on command line to execute that specific task. So the first one is to build a container. And the second one is actually just executing Jupyter CLI and passing it passing it as the input, the IPYNB, the notebook file. Second one is using SAS via CLI to submit the SAS code to via environment. Third one is again executing Jupyter on CLI, passing it the notebook. And the last one, yet again, Jupyter notebook is getting executed on command line. And thank you. I'll be happy to take any questions at the end. And hopefully this was helpful. Thanks.